The topic of this section is about error correction. We first try to introduce the concept of code words. A frame consists of m-bit data and r-bit redundancy bits, or we call check bits. So the total length of the frame, which we call n, it equals to m plus r. So this n-bit unit containing data and the check bits is often referred to as an n-bit code word. Given two code words, we can determine the difference between these two code words based on the number of bit difference. The number of bit positions in which two code words differ is called Hamming distance. If two code words are a Hamming distance apart, it will require these single-bit errors to convert one into the other. We can just use exclusive OR to exclusive OR these two code words, and then count the number of ones in the result. We can construct a complete list of legal code words, and then we can try to find out the two code words whose Hamming distance is minimum. This distance is the Hamming distance of the complete code. The error detection and error correction properties of a code depends on its Hamming distance. In theory, in order to detect d-bit errors, we need a distance of d plus 1. But when you want to correct the errors, we need a distance of 2d plus 1. So now we try to say how we can use Hamming code to do 1-bit error correction. We call it 1-bit Hamming error correcting codes. So imagine that we have an n-bit code in which we have m-bit messages and r-bit check bits. And we want to detect and also correct all the single error. The first thing is to try to figure out the relationship amongst n, m, and r. There is a formula here to do 1-bit Hamming error correcting. The m and r and n, they should satisfy the formula like that. M plus r plus 1 should be less than or equal to 2 powers r. For example, if we have 8-bit message, in order to do 1-bit error correction, we need to have 4 bits redundancy bit. The bits of the code word are numbered consecutively, starting with bit 1 at the most left-hand side, bit 2 to its intermediately right, and so on. After we numbering all these bits, then we need to find out which bits are message bits, which bits are redundancy bits or check bit. So we say the bits that are powers of 2, they are check bits, such like bit 1, bit 2, bit 4, bit 8, bit 16, and so on. The rest bits, we call it message bit. So the message bit should be filled up with the m data bits. After we figure out which one are message bits, which one are check bits, we need to think about how we specify the value of all these check bits. So each check bit forces the parity check of some collection of bits, including itself. It depending on whether you do even parity check or order parity check. So the question now is, which bits are the collection of bits you want to use? A bit can be introduced in several parity calculations. For example, bit 11. So 11 can be represented as 1 plus 2 plus 8. So the bit 11 will be used several times for the parity check bits number 1, number 2, and number 8. So this is what happened on the sender side. So the sender do Hamming code to convert the original frame to the Hamming coded frame. When the receiver received it, receiver also need to do some operation to check whether there is an error. If it is something wrong, it need to be able to correct it. So here comes the algorithm for the receiver side to do Hamming correcting error. The receiver needs to initialize a counter, and the counter should be initialized as 0. And then the receiver needs to examine the check bits. Check bit 1, check bit 2, check bit 4, 8, and 2 powers k to say whether it has the correct parity bits. If it is incorrect, the receiver should add the number of the bit k to the counter. So after the receiver goes through all this algorithm, the receiver will check the value of the counter. If the value of the counter is 0, it means it is a valid code, nothing gets wrong. If the counter value is not 0, it means we get something wrong. And then the receiver should do error correction. The value of the counter denotes the number of the incorrect bit. So the only thing the receiver should do is simply to flip the number indicated by the counter. We have an example here. If the receiver now receives a code words 00111 000100, the question now is the code correct or not? If it is incorrect, what is the correct one? So we try to sort out this example because now the total length of the code words is 11. And among these 11 bits, 7 bits are message bits, 4 bits are the redundant bits or the check bit. So we can easily know the first bit, second bit, fourth bit, and 8 bit, they are check bits. So the receiver just needs to recalculate all these 4 bits. So we go through these 4 bits, we find out bit 1, because now we do even parity check for bit 1. We count out there are 3 ones, which means it is wrong. So we add the value 1 into the counter. For the second check bit, again, we only have 1 1. So again, we need to add 2 in the counter. The fourth one, it is correct. Even parity check, we have 2 1s. The 8, again, it is wrong because we only say 1 1 here. So we add 8 into the counter, and the counter value, it ends up with 1 plus 2 plus 8 equals to 11. So it indicates the 11th bit is wrong. We need to change that bit from 0 to 1. So the correct code word is 00111 000101. We simply convert the last 0 to 1. So in the end of this section, we have 2 questions. First question, why Hamming distance should be d plus 1 if we want to detect d-bit errors? And why it should be 2d plus 1 for correcting d-bit error? The second question is, for Hamming code, why the code word should satisfy m plus r plus 1 less than or equal to 2 powers r? How can we figure out this formula? So that's 2 questions for you to think about. That's it for this session. Thank you.